Right, so let's get started. It's 10:30. So welcome to ME 545. Hopefully you're in the right classroom. Hopefully I'm in the right classroom. This is my fourth year teaching it. My name is Thomas. I'm a PhD student, so you don't have to call me professor. You just call me Thomas. Calling me professor makes me feel old. And yeah, so I'm very excited. Anyway, I work with Professor Shu Chen at Max Lab in the mechanical engineering department, and my specialty is disturbance rejection and disturbance observer design. How many people here are first year students, first year grad students? Okay, so more than half. Second year? Third year? Nope. Master students? Most of you. PhD students? Very few. So anyway, yeah, let's just get started. How many here are taking controls for like as elective, just for fun? Okay, and then out of interest for your field? Okay. For the master's program? I'm not sure if they changed the requirements, but I think you can just pick classes that you want to take, and if you get the minimum credit, you can graduate. But if you're taking controls for fun, it's kind of like a masochist move. It's a lot of math, unless you like math. So yeah. Yeah, I'm glad you all came in person as well, so I appreciate that. It's a lot easier teaching in person than at blank screen, but this class is going to be also hybrid, so if you're not feeling good, you want to stay home, you can attend online. So on Canvas, I guess I'll start sharing my screen. If I can get Zoom to open. There you go. On Canvas, you can find the link to join the class online. All of it's going to be recorded and uploaded online as well. So if you miss live session, you can always just watch it later. For navigating Canvas, the way I have this class set up is I like to use modules to kind of break up the class into week-by-week basis. So if you do fall behind, you can know which week, how many weeks you have to catch up. Please don't get to that point, but if it happens, it happens. I understand. So you can go to modules. You can see that we have all of these partitioned by week 1, week 2. And yeah, I'll upload the lecture right here. And if you click next, I'll have the corresponding lecture material for you to download and write on, so you don't have to write everything I write out. The way I have it set up is that you can actually put like 4 lecture slides per page, so you can also save paper, because there's going to be around 180 pages of lecture material, just to save pages. And I'll also upload my annotated notes if you're not into writing in class and just want to listen as well. That's completely fine. Please read the syllabus on like homework policy, but TLDR, I will drop your lowest homework grade. So if you're falling behind and you just don't want to do homework, that's fine. If you turn in homework late, it's a penalty of 10% per hour late, up to 50%. So if you homework's due at 11:59, if you turn it in at 12:30, that's 10% off. But you know, if you want to just get some sleep and just take the hit, you have 24 hours after it's due to turn it in. Once it's past 24 hours, I'm gonna upload the solutions, so it's no longer viable. Just so you can review the solutions. Let's see, what else? What other logistics stuff do I need to do? 2 exams. When I was an undergrad, I swore I would never do 2 exams or 2 midterms in a quarter system, but I understand why they do it. It's too much material to test if I had 5 weeks of material in 1 midterm to do in 50 minutes. So while it has the name midterm, think of it more like quizzes. It's only worth 12.5% of your grade each midterm. So even if you do poorly, you'll be fine. The homework grade will cushion that blow. And the second midterm, usually people do better because they get into the pace of things, so it'll be okay. And since this is my 4th year teaching, I'll also release previous year's exams so you can see how the exams are like in paste it yourself. I'll also release the solutions because I'm pretty confident I can make it different enough. But if you get the general idea of the exams, you'll do well. I have not failed a single student yet, and I really don't want to fail another student this year, so don't freak out about it, okay? Since you're all here in person, this pertains more to the online section. If you are in section A or B, but you work full-time or cannot make an exam, please let me know. I have an online version instead, and I'll have more details on how to do that just for the online section. The way you can check is that if you go to people, you can see which section you're in. So like me, I'm in all three sections, but you can see which section you're signed up. If you're in section C, you're good. I have you on the online exam already, but if you're in section A or B and you cannot make a midterm for whatever reason, please let me know and I can add you to the online exam. Not wanting to come in to take the exam is not an excuse. It has to be like work or you're sick or something like that. One other thing, I have updated the calendar. I'll also upload the office hours. If you go to course calendar, you can see our class time. You should be able to join through here as well. You can also see the dates for when homework is due. So sorry, there's a homework due next Thursday. It's short. Shouldn't be too difficult, but I'll start hosting office hours next week. We have 2 TAs, Yusen and Zedong. They're not here right now, but I'll have them post their office hours as well. So we'll have office hours most likely Monday through Thursday. Homeworks I do Thursday, so you can just take your Friday off and enjoy your weekend. Let's see, anything else before we get started? Any questions? Yes. 9. Yeah. This is a 4-credit class. The amount of material we have to cover is pretty extensive, so homework is really important. It's going to be a mix of solving things by hand and a mix of using either MATLAB, Python, Julia, or whatever your programming language you like to use as well. During Thanksgiving, that's when it's not due. You have 2 weeks for that, and that's homework 9. I might have a homework 10 as extra credit. I don't know. I haven't decided yet. We'll just see where things are at by that time. Usually people are dead and don't want many more homework, so it's understandable. So I might make it extra credit, like a homework 10 if you want. Yeah. Any other questions? All right. I guess we can get started. Stop sharing. So when I say control systems, what pops into mind? Like when I say controls, what do you think of? It's a very vague question, so I guess it's kind of hard, but what pops into your mind when I say control? Yeah? Thermometer. Yeah, like AC in the spring, but we're semi-comfortable temperature. Yeah? Yeah, if temperature drops too low, heater turns on. During the summer, temperature goes too high, there's no AC, so in the MBB, so you just stuck. Yeah. Any others? Yeah. Cruise control. Yeah, great example. Yeah, cruise control is great because if you have to go on a long road trip and you don't want to just be constantly using the throttle, you use the computer control that. When you look at that, we have a desired input, right? We set our desired input, which is speed, and then the engine and computer will work together to get the car up to the speed, and then our desired output should match our input. And it uses error as feedback to correct any mistakes. One more. Yeah. Line following robots, yeah. I don't have as much experience with that, but yeah, I mean, it's the same thing. You have a reference input or a reference trajectory, and the output is going to be looking at where it's actually at, uses there to figure out the difference, and then it'll try to close that gap. Are unstable systems bad? And because I'm asking, it might be a trick question. No. Who said that? You said that. Why? I don't want to put you on the spot if you don't know. Yeah. Exactly. Exactly. Unstable systems are fine if we can control it. If we cannot control it and still unstable, then it's bad. Yeah. Just because we have a stable system doesn't mean we want that to be stable. Unstable systems are easy to move, right? If we think about like an inverted pendulum, does have this ruler, just grabbed it from my office. And like it's pretty unstable, right? Because it just wants to tip over. But it moves very easily. If I were to just put it on the ground, it's not going to move. I mean, if I kick it, it'll move, but there's a lot of friction to overcome that. Me standing, I'm a inverted pendulum, right? So walking is very efficient because I'm using gravity to make me move. But if I were to be like the ruler, I'm on the ground, it's going to take a lot of energy rolling around. I'll never fall because I'm stable, but it's a lot of energy. Walking is nice. It's unstable, so sometimes I'll trip, but it's a trade-off. And we humans have evolved to walk because it's very energy efficient. So when I say control systems, I think one thing you should think about is you want to use some input to get your desired output. But at the end of the day, control system is an optimization problem. Sometimes you want to minimize input energy and you want to maximize your output. You want to save energy, but you want to get what you want. Sometimes you want to get your output, you want to get to your output as fast as possible, so we ramp up the input energy. And that could be an optimization problem too. It depends on what you want. So it's a optimization problem. All right. Let's get started on the official lecture slides. I'll dim the lights. So if I see that better, share my screen. Give me a sec. Go. Is this the right one? Yeah. Okay, so today we're going to start with the introduction. This is going to be chapter 1 in your textbook. Oh, by the way, I don't require a textbook. If you don't want to buy the textbook, that's completely fine. If you want to use older editions of the textbook, that's also fine by me. The chapters more or less are in order. I think edition 6 and onwards should match what I have on the syllabus in terms of chapter subsections. So we went over the course logistics. I'll talk about course goals. Then we'll go to chapter 1 and then jump to chapter 5. It might seem kind of out of place, but I think this order will make more sense later in the quarter. Chapter 5 is on block diagrams, so you don't need to know anything about stability or things like that. But I want to start with that. Let's see. So yeah, reference textbook is Control Systems and Engineering by Norman S. Nice. Any edition works. You know, if you can find an online copy, I'm also cool with that too. 9 homeworks, 2 midterms, and 1 final. This will be in class unless you are online. Then it'll be online for you. The way the online exam works is that I'll have like a 3-day range where you can open the exam. But once you open the exam, the timer will start. If you close the browser, the timer will continue with or without you. Complete the exam, then you upload it. Obviously, do not work with other people, especially for the online people. This is an honor system. If you cheat, it's unfair for people who take the exams in class. So please don't do that. And I'll pass. Like, I've never failed a student before, so don't freak out about grades. You're in grad school, unless you're applying for a second grad school, which I don't know why you would do that. Grades aren't that important here. So here are my course goals. I want you to know how to model systems in the time and frequency domain. I want you to know how to assess the stability of these systems. There will be multiple tools that hopefully you'll learn by the end of the quarter of assessing stability. Some will be more appropriate than the others. Determine system response for various inputs. So if I say I want to give a system a shock like a hammer, like that's an impulse input. Maybe I want a continuous constant input. I want you to determine how the system will behave based off of these inputs. The big one is understand what each component of the PID controller does. I think 90% of control industry uses PID controllers because it's just so good. It's very robust, but it's also a century old. If you want to get really high performance things, we move away from PID controllers to very specific controller that's designed per case. And prepare you for advanced control courses and reading research papers. This is also a big one, especially for PhD students here. And since most of you want to take controls as a focus, this is the foundation. Just a word of caution, we have 10 weeks, 10 and a half weeks maybe, well, more like 10 weeks because we get Thanksgiving off. There's 10 chapters to cover, which is a very, very aggressive pace. That's roughly, we're gonna be covering this much, okay? I've read this whole textbook, so you don't have to, and I've cherry-picked the things I found important from reading papers and specifically courses at UW. So there might be things we'll skip in the textbook. There are things that are very outdated that I'm going to skip because I'm ending the cycle of abuse. In the past, when I took this class, they had me learn Routh-Hurwitz criteria, and I'm like, I've never used that in my life. Ending that cycle of abuse, we're not learning stuff like that, but I'll teach you the more relevant material. I'm biased. I'll say all the chapters are important, but if you really had to focus, please focus on chapters 3, 4, 9, and 10. These are the most important chapters, but if you can, please focus for all the chapters, but I know, like, it's tiring. We will cover classical control theory, which is modeling linear systems. In the real world, everything is nonlinear, so it sucks, but to learn nonlinear systems, you need to first learn linear systems. So this is your foundation. And once you learn linear systems, then you can move on to nonlinear systems. So let's start with the introduction. Any questions? All right. So I just want to show you some cool videos I saw online. If I can. Okay, well, maybe not. If this works. Oh my God. Well, it's a cool video. So you can click on the link. Well, actually, let me try for my laptop. I'm committed to this. So I swear you'll like it. There you go. So this is an example of robust control. So we have an inverted pendulum. And in this model, it's just a model of a rod. And if you hit it with a stick, it's rejecting disturbance, which I think it's pretty neat. And now this is modeling error, but there's no model of this mass on top, but the system is robust enough to compensate for that and stabilize the system. This one's also pretty cool. As they add water to it, the mass is constantly changing, but the system's able to compensate for it. Pretty cool. It's a very nonlinear system because if you think about it, the rod angle will change and the force will change based off of the angle because it's going to be related to sine theta. The more horizontal you get, the greater of gravitational force you have to overcome. Okay. Now, this one's a nonlinear control. If you thought that was cool, you'll be wowed by this. It's a triple inverted pendulum that's able to up itself, just like that. Oh, yeah? What? Well, actually, it wasn't double? Oh, I got the cooler one. Which professor was that? Or who was that? Brunton? Yeah. Oh, yeah, yeah. It's actually where I got this idea from, was from Steve Brunton. Yeah. Oh shoot, I think online people didn't see the video. Oh well. Um, so yeah, if you didn't see the video for the online folks, you can just click on these links and you can see the inverted pendulum control. So we use modeling to predict behavior. And the thing about models is that all of them are wrong, but some are useful. And what? That all models are wrong, but some are useful? What does that mean? Well, like with that pendulum, I'm sure they didn't model in friction with the inside the motor, or maybe the rod they said was 100 grams, but weighed 110 grams. If the model's close enough and you can kind of anticipate how it's going to behave, and then you use feedback to correct where it's actually at, then your correction doesn't need to be that big of a correction. So models, all of them are wrong because they're all estimates of real systems. If you try to model something 100%, it's going to use a lot of computational power. Controller might be too slow to respond. So you want them to be close enough and you want them to be useful, because you can have the most accurate model, but then it just bogs down your computer and you can't run simulations, or you can't run the controller. The controller can't keep up. It's not very useful then. The way we use modeling is we use physics. We use physics to as like our basis. We can like free body diagrams. Anyone here taking Steve Shen's class 588? Yeah, so you're going to be doing a lot of free body diagrams and using physics to derive your models. You use this to derive differential equations for linear systems. So we derive differential equations. I'm thinking, should I do this example? Yeah, why not? So like if we were looking at that inverted pendulum and we have our motor, and we'll just do a single pendulum. I do not want to derive the differential equation for a triple pendulum system. We have mass M here. We have gravity working on it. And we're going to set our reference angle to be there, to be vertical. This rod has a length L. And our input is going to be the motor that controls this rod. So I'm going to call this rotation here U, which is our input torque. Can you guys see this okay? Yeah, okay. Yeah, anyone in the back see this okay? Do you want the shades closed? Okay. Let's see, raise shades. Oh, lower shades. This is the most advanced class I've ever had. Then let me try that. How about that? Oh yeah, that's better. Although if you're feeling seasonally depressed, let me know. I'll open the shades. Okay, so we'll use physics right here. So let's say the sum of torque, because it's input torque. So sum of torque is equal to, and you don't have to remember this, but your inertia times your angular acceleration. And I guess it's like a little hand wavy, but it's just going to be your mass times your gravity. But then it needs to be acting in the vertical direction. So it's times your length times sine theta plus u. And that's it. That's your differential equation. It's nonlinear because of the sine theta. So theta is, if we're tracking our angle theta, it's going to change the torque in a nonlinear way. Yeah, just an example of a model. We have not accounted for friction. We haven't accounted for any very slight aerodynamic effects of this thing swinging down. We don't need to. It's negligible. Any questions? Should be pretty straightforward, hopefully. High school physics, right? One thing I want to talk about, because even though we're talking about classical control systems, we do need to embrace the future. Things are heading towards machine learning and big data, these buzzwords. But we always have to start at the fundamental, where we start with model-based systems and model-based control. And, you know, everyone wants to go to model-free because it's easy. You don't have to use free body diagrams and derive differential equations. Model-free means just giving it input data, of random input data, and seeing what the output looks like, and then just drawing correlations. They're great because you can apply to nonlinear systems, but you need to know what you're seeing, and there are times where it's better to use model-free. There are times where it's better to use model-based systems, or where you do a mix. And when you do a mix, you need to understand both of these components. So something like model predictive control is model-based, where you use common filtering, you guess what the next state is going to be. Learning MPC, reinforcement learning, and imitation learning all have model-based systems, but it becomes less and less dependent on that and more dependent on data that you feed in. And if you look at large language models like ChatGPT, those are model-free systems. So this is the future we're heading towards, but it's still important that you learn the fundamentals, the foundation, because just like if you want to learn nonlinear systems, you got to learn linear systems first. Okay. Originally, in the past, I've had an example of modeling, but I'm going to try this year, try something different. Anyone want to give me a random system to model, and we can brainstorm this together? This might be a little risky, but any brave soul want to offer something like a control? It can be anything: biological, mechanical, rocket ship. I had a feeling someone was going to say a rocket ship, but okay. So we have a rocket ship. This is a terrible drawing. Okay. We don't want that rocket ship to crash, right? So we should be tracking what should we be tracking? Like the position of the rocket ship, right? But what specifically about the position? The pitch, yeah. To simplify it, maybe I'll just say we'll just track one thing, because we're going to do a single input, single output system. Otherwise, it's going to get very complicated. We're going to assume everything else is perfect. Our velocity is good. Everything else is good. So we're just going to track the angle of this rocket. And let's say the rocket's pointing this way. That's the angle. So our input is going to be desired angle. And then that means our output, and let's say we're using gyroscopes and IMUs to, well, not gyroscopes, but IMUs to track the output angle, then we're going to get actual angle. And this is only in one plane, so it's very, very oversimplified. What are the main components that make a rocket? Like the very, very big components. You don't have to tell me about like the fuel tank or anything, but what are important components of making a rocket fly? Nozzle. So like, yeah, the nozzle for thrust, right? Nozzle. How do we track the orientation? Gyroscope, like with sensors. So we'll say sensor, like a gyroscope. IMUs. Okay, we need a brain for this rocket, right? So what do we need? A what? Flight controller, yeah. Flight controller. Um, and we can keep adding more components to make this model more accurate. Let's add maybe one more component. And I may specifically focus on the nozzle, right? How do we control a nozzle? I actually don't know how nozzles work, but maybe we can make something up. Gimbal control, yeah. So that's going to, so gimbal kind of like, so it stabilizes it. Yeah. Well, let's assume that's already stable, right? How do we move the nozzle with a motor, right? With a motor. Perfect. Yeah, that'll be good. Okay. So what I'm going to draw, and this is going to be what we're covering soon, is a block diagram, which is covered in chapter 5. But for now, maybe you can just follow along. Hopefully it'll make some intuitive sense. So basically I'm going to have, basically a block diagram is going to be this, where I have my input, I have my system to be my system, and sorry, make that neater. And I have my output. And so I have an input, goes into my system, and then it reacts, and that it now has an output of some sort. What we're going to do is we're going to expand this single block into multiple blocks now, into individual subcomponents. So my input, so on the left side, it's going to be my angle. This is my desired angle, and maybe I'll say it's desired. Might not be the actual angle that we have, but it's our desired angle. And we're going to feed that into what? Anyone want to take a guess? Yeah, you could put, yep, exactly. So yeah, exactly. Put it into a controller, because if I just tell my motor to say, like, I want it to go to this angle, it won't understand that. So the controller translate that signal into something that the motor understands, like voltage, or I don't know how rocket engines work, but something like that. So let's say, I'm going to say flight controller, I'm going to denote FC. So then now it converts the signal into something that the motor understands. So then we're going to feed this into our motor or our nozzle. And we can, if we want, we can actually even break this nozzle down into subcomponents. Say inside the nozzle, we have the controller, like self-contained controller, which receives that signal, then it's going to tell the motor to move to this location, something like that. But we're not going to do that. So it feeds it into the nozzle. And basically, so the nozzle is going to, the output of the nozzle, let's say, is going to be like thrust. So then we're going to apply this amount of thrust to our rocket at this angle. So I'm going to say, I'm just call our main rocket body here. It's going to be here. And then, and within our rocket, we have our sensor. Inside this, we have our sensor. So then our output for that sensor is going to be, output is going to be theta. It's going to measure the actual angle. Something like that. So it's a very, very simplified model. This is how block diagram works, where we take the single system and we break it down into multiple subcomponents. Any way we can improve this? Like, how do we take this output and feed it back. So we can use sensors, yeah. So we create a feedback system. So then we now have the actual measurement. So we want to take this measurement signal. And here I'm going to just draw a circle. And we're going to feed it back. So now essentially we're taking the output and we're comparing it to the input signal and seeing the difference. So this point here is called our error, which is going to be the difference between our output minus our input. This is a very, very simple feedback system. Sometimes what you might see is, let's put a block here. Because I heard someone say sensor. You're right. Let's say we will actually have our sensor here, which then takes this into a signal that is, I guess, the same units as the input. And that's going to be our feedback system here. Are there any questions? So this here is called a block diagram. And we'll be covering that. And that's chapter 5. Right. So this is a highly simplified model. It's oversimplified. If we try launching this rocket, it's going to crash. But I mean, we don't account for drag. So like no drag in the model. We don't count for like uncertainty. No uncertainty is accounted for, like uncertainty in our motor. If our motor says we're creating, like if our nozzle is creating 10,000 pounds of thrust, that's what we think we're telling it to do, but it's actually putting out 10,500. We don't know that. So it's overly simplified. Usually the block diagram for something like this would be way more complicated, but you get the idea. Anyway, so the purpose is to control the plant to get desired output. That's what I'm trying to take away with this point. And here's some definitions from chapter 1. So a control system is an arrangement of components forming a system that will provide the desired response regardless of any external changes. And then, so that control system is going to be like that single block with our input and our output. And then the plant is the subsystem where the output is being controlled by the system. So in the above example, our plant is going to be the nozzle plus the rocket, which is controlled by the flight controller. So the plant is the system to be controlled. Sometimes the way in the textbook, it might denote it like this, where we have our input, and then it's going to put the C here. And you'll see in the textbook it says C of S. The S here is just to denote the domain it's in. Just don't worry about that for now. And then we have P of S. So the C stands for our controller and the P stands for the plant. So here we have our plant, and here we have our controller. Any questions? Yeah.
Is the sensor a part of the plant?
Yeah. It can be. So when I say that, sometimes and maybe I'm jumping ahead a little bit. It doesn't have to be, because sometimes, like, let's say we have our plant P and we have our output, and then we have our sensor here, and usually we denote the sensor H. So this is the feedback. And then we have controller C here. So the plant is still P here, and our sensor is not part of the plant. But the way you can arrange it is you can get an equivalent system to look like this through some. Oh, question online is what was H? H is the sensor. We can get this into I call it PEQ, which is like the plant equivalent, and we have the sensor embedded within the plant. Sorry for my bad lines, something like that. So we can actually take this plant and we can put it into plant there. So that's what, in that sense, the sensor is now embedded into the plant. In our physical system, nothing's changed, but our graphical representation has changed. Usually we do this because a lot of equations use this form here over this form. So these are, I mean, both of these are fine. And our equations might use one or the other form. So we usually like this form on the right for analysis. It's a lot easier.
I have another question, sir.
Yeah.
Is it okay to get disturbances in the controller because of the plant?
Yeah, so sometimes the question is it okay to get disturbances? Well, we don't want disturbances, but it's unavoidable. Sometimes we can have a disturbance appear here. Disturbance can appear here. Disturbance can appear here before the plant. Maybe the controller has some weird cabling. Yeah, sure, cabling, like static. Disturbance can appear here. We can also have disturbance appear before here too. This is how we model it. We identify the source of disturbance and we figure out where it's entering the system, and then we just throw it in there. So those are all possibilities as well. If I do that, I should put a plus sign because we're adding disturbance into the system. Yeah. Okay. So we're just going to go through a few more definitions for in chapter 1 before moving on to chapter 2. If we look at open loop systems do not compensate for disturbances. Like the reason why we like them is because they're cheap and simple. We don't use feedback. Anyone can think of any examples of open loop systems? Yeah. Oh, toaster? Yeah, exactly. Toast is burnt. Anyone burn toast? Yeah. I mean, you could become the feedback yourself, where you go look at the toast, and if you see it's brown, then you click cancel. Then you're the feedback now. You're the sensor. But if you just click toast and you just, I don't know, go watch TV or go do something else, that's an open loop system. 3D printing, anyone ever have bad prints? Leave the room and come back and see your prints all messed up? Yeah, open loop systems. The printer doesn't know it's doing a bad print. It'll just keep doing whatever it's told. So they're cheap and simple, but it's kind of a hassle to deal with because you have to be monitoring it. Now, if we look at closed loop system, closed loop systems uses feedback to correct for error. And error is going to be the difference between the input and the output. So earlier I kind of alluded to that, but our error is going to be here. Error, which is equal to the input minus in this situation, it's like the sensor output. Because maybe this output versus this output is different. So this is the sensor output. I mean, usually it's just converting a signal to a different signal, but they're both the same signals. But then, yeah, maybe I'll have disturbance at the sensor that contributes to error as well. It's more complex and expensive than open loop systems, but we like it. We like it for our cruise control, so our car doesn't drive too fast. Have you ever used cruise control on a hill? You notice how it corrects it, but it doesn't know there's a hill. So car will slow down. The error is going to be, oh, we're slowing down. So our speed is maybe 55 miles per hour, but our set point is 60 miles per hour. Error is minus 5 miles per hour. We'll add throttle to get back to 60. Yeah, so closed loop systems are nice, but they are more complex and expensive than open loop systems. Sometimes when you add feedback, you can also make a system become unstable. So there's also that added level of complexity. We'll talk more about that in chapter probably 4. But then with that, then you can do PID tuning to make it stable, because sometimes throwing a PID controller can make something become unstable too. All right. Any questions? I wonder if we can get to finish chapter 1 today. That'll put us right on track for 10 chapters in 10 weeks.
Question.
Let's see. So when we look at our output, we have it's called the system response. So the output response of a control system goes through a transient response before reaching steady state. So transient meaning the response is dependent on time. Steady state means it's no longer dependent on time. Let's say if I were to, there's a question online. Oh, I missed the question.
Can you hear me by chance?
Yeah, let me hold on a sec. Somehow I can't hear you. Let me turn you up on my laptop. Can you repeat that question?
Yes, on the it's related to the previous slide. So where here could you put some sort of predictability to confirm whether you're getting closer to the actual correct output?
Where can I put predictability?
Like a guess.
Guessing. Oh, yeah. It's kind of like common filtering where you have I don't have that off the top of my head, but I can try, right? So sometimes what we can do is we can take this input signal and we have our estimated system. And I guess this might not be as good of a model, but our estimated system, and then we get our estimated output. And then basically what we want to do is we want to then take this output here. Oh, well, I guess I put it through the sensor, right? Take this. And we can either subtract it or add it, but then we have to either add it or subtract. So we maybe, actually, then this no longer becomes our estimated output. So here, this is our estimated output. Then we get our error. Then what we're going to do is we're going to take this error and probably feed it back to adjust our input command. Something like that. It's not going to be exactly accurate, but if you want to look more into that, look into common filtering. That's one instance where they take what you do is you take your output and you try to guess what the next output will be. Then you compare your guessed output versus the actual output, and then you adjust your parameters to get closer and closer, so your estimated system becomes more accurate. What you're also thinking about, I think, might be related to that is MPC, so model predictive control, if you want to read more into it. These are both outside the scope of the class, but this is going to be covered in 547. ME547, which is going to be taught next quarter. This one is just more like, if you're interested, you can look into it. Does that answer your question?
Yes, it does. Thank you.
Okay. Okay. So when we look at our output of our system, oh, it's already 11:20. All right. We'll pick up on this tomorrow. Hold on.